Hello everyone and welcome to the channel. So today in this video I will be talking about the Great Orthogonality Theorem, okay, which is called GOT also. And this is very important because previous few years, like in 2017 December and in 2017 June CSIR exam, they are asking about this, asking like questions from here, Great Orthogonality Theorem, okay. So and in this video I will be also solving few questions based on character table, which most of you have asked me to solve questions on this. So that's why I'm going to solve in this video, okay. So this video will include a brief review of this Great Orthogonality Theorem, and there will be problems solved based on character table which are asked in previous 2-3 years of CSIR exam, okay. So before going to this video, before starting the video, I will suggest you that if you haven't watched my previous video on character table, that how to solve a character table, you should go and watch, okay. There will be the link for that, and you should watch that video. Then only you will be understanding how I am going to solve questions, okay. Because I will not be going in that detail here. I will be just solving the questions, and all the details are there in that video, okay. So it's better if you haven't watched that video, go and watch it, and then you will be understanding this video more easily, okay. So let's start. Okay, so the mathematical form of this Great Orthogonality Theorem will look somewhat like this, okay. So this is the mathematical representation of this theorem, and for the exam point of view, for the CSR point of view, this equation won't help you much, because like you cannot determine anything from this equation itself, okay. So you don't have to remember the equation. Just for the sake of information, I'm just telling you, okay. And a few variables here like r represent the symmetry operation. This lambda I and lambda j, this lambda represent the character, okay, the characters which are given in the extreme left side of a character table, okay. Sigma is the summation, means sum of all these things. H over here is the order of the group, okay. And li and lj are the dimension of the symmetry operation. So this is just a introduction to this orthogonality theorem, okay. But the main thing, the important thing is the rules, okay. So one by one we will talk about the rules here. Okay, so without wasting much time, let's quickly talk about the rules, okay. So the first rule of the Great Orthogonality Theorem, it says that the number of characters in the character table will be equal to the order, okay. So it depends on the on what character table you are taking, on which point group you are taking. So the number of order in that point group will determine that how many characters will be required for that character table, okay. So this is also like it's just the beginning of it. Second rule says, and this rule is very important, okay. So this rule is only applicable for the identity, okay, identity operation. So it says that the value of identity in all the characters is such that the addition of a square of them is equal to the order, okay. So let's say we have a character table of, let's say we have a character table for C2V, okay. If you have seen that character table, you would have seen that there are 4 characters, A1, A2, B1 and B2, okay. And we have the or like the symmetry operations identity C2 and sigma xz and sigma yz, okay. So like this we have, and for identity we are having 1 1 1 1 like this. So if you will add square of them and add it, all the value of identity in all the characters, if you will add them, okay, so what you should get, you should get the order of this. So order of this is 4, because there are 4 different operations, so the order is 4. So therefore you will square them, so you will get 4, that's it. So if that is valid for it, okay. So it is valid for all the character tables. So it says that the value of identity in all the characters, okay, in all the characters is such that the addition of a square of them, if you square and add them, is equal to the order of the character table, okay, order of the point group for which the character table belongs. Now the most important rule is the third one, that is orthogonality of two characters. Means that we have two characters, let's say like A1 and A2, okay. So it says that if two characters are multiplied, like they are orthogonal to each other. Means if we multiply these two characters, the value of these two characters, we will get 0. How? Let's verify this. Let's multiply these two, okay. So 1 into 1, that will 1, plus 1 into 1, that will be 1, plus 1 into minus 1 will give you minus 1, plus 1 into -1 will give you -1, so you will end up getting 0. So this is the orthogonality of two characters. Okay, the next one is, okay, so this was for a1 and a2. Similarly, if you will take a2 and b1, then also if you multiply all the values of different symmetry operation, then you will get 0. Okay, and similarly for means any two of, if you will take any of the two characters and check, they will be orthogonal to each other. So this was the main thing for the great orthogonality theorem. Only this thing you have to keep in mind, mainly this one and the rule number 2. Okay, this is going to help you in solving questions from like previous year's question. Okay, so now we will be solving the questions which were asked in the previous year of CSIR exam, and we'll try to solve them using great orthogonality theorem and the character table, which I have already done in my previous videos. Okay, so let's start that thing. Okay, so let's solve the question which was asked in December 2017 CSIR exam. The question says that the part of character table of point group, it is given, order is also given 4, and order is given because you have to use the great orthogonality theorem. That's why they have given you the order. Okay, so it is asked that what is the value for this lambda 4. Okay, so let's check it out. See, using rule number 2, first of all, rule number 2 tells that for identity, if you will square all the values of all the values of identity and add them, then you will get the equal to order. Okay, so if you will solve that, and you will get 1 square plus 1 square plus 1 square plus 1 square, means fourth value should be 1 only, then only you are going to get 4. Okay, so here at this place it should be 1. Okay, and like see, this question was very simple. This was C2B point group. If you remember the point group, if you remember the that character table, you would have done it easily. But then also I'm just verifying it using the orthogonality theorem. Okay, so at this place it should be 1. Now this 1 is available only in option 1, 3 and 4. So option 2 cannot be correct option. Let's cross it out. Now we have only 3 options left. Now the other rule says that they should be orthogonal to each other, means this term should be orthogonal with this term. That means here is 1. Okay, so let's write 1 over here. So now let's do it. Let's write it x, y and z. Okay, so this may be x, y and z. We don't know them, so just multiply them. So you will get 1 into 1 plus minus 1 into x plus minus 1 into y plus 1 into z, that will be z, and this should be equal to 0. That is from the rule number 3. So that will be 1 minus x minus y plus z is equals to 0. This is equation number 1. Similarly, you can form one more equation using lambda 4 and lambda 2. That equation will be 1 minus x plus y minus z is equals to 0. That will be equation number 2. And similarly, one more equation you can form from lambda 4 and lambda 1. So that will be 1 plus x plus y plus z is equals to 0. That will be equation number 3. Now in order to check what will be the values, you don't have to do anything. You just add this first and third. When you add these two, what you will get, this 1 plus 1 will become 2, this x will cancel out, this y will cancel out, and z plus z will be 2z is equals to 0. So you will get 2z is equals to minus 2, so z is equals to minus 1. So you are getting z is equals to minus 1. Now that is available in option 4 and option 1. So either your option can be 4 or 1. 3 is also cancelled out. Now let's check out. Now just add equation number 2 and 1. And when you will add them, what you will get? You will get 1 plus 1, that will be 2, and minus 2x, okay, plus, means y will be cancelled out and z will be cancelled out, and is equals to 0. So 2x will be equal to 2 and x will be equal to 1. So here it should be 1. So what you have got, 1 1, why we don't know. So 1 in 1 and 4 option 1 you are getting at the place of x in option 1. So you don't have to solve it further, but if you want to solve it further, you can just put the value of x and z in any of them and you will get the value of y. So the correct option will become option number 1. So like this, in this way question will be solved from CSIR December 2017 exam. Okay, now let's take few more questions. Okay, so this question, it was asked in CSIR June 2017 exam, and it was also based, it can be also solved with the help of great orthogonality theorem. and it asks you that the missing place what should be. Okay, so it is asked for a complete group, and incomplete character table was given below with one reducible representation missing. This is missing over here. Okay, so what will the Mulliken symbol and the characters missing? Okay, so let's try to solve it. First of all, try to check the order of what will be the order of it. So for E the value is 1, and for C3 it is 2, the coefficient. Okay, I'm talking about the coefficient. So for E it's 1, for it's C3 it's 2, for sigma V it's 3. So overall you will get 3 plus 2 is 5 plus 1 is 6. So order is 6. Okay, so I'm just writing order is equals to 6. Now it says the rule number 2 says that the sum of all the square of the value of E will give you the order. Means 1 square plus, let's say we don't know that. Okay, and the square of that term means x square. Let's take it x plus 2 square is equals to 6. So 1 plus x square plus 4 is equals to 6. X square is equals to 1. So x can be 1 plus minus 1. So x can either be plus 1 or minus 1. Now one more thing you should know that E, the value of E cannot be negative. Okay, so it cannot be minus 1, it should be plus 1. So here what we have got is 1. In all the options we have 1, so it doesn't help much. Now let's check out using the other one. Okay, so by now we have got the value of x from here, and we have to find out these two. So let's write it as y and z. Okay, now let's use the orthogonality theorem. See, in the previous option, in the previous question, there the coefficient were 1 only, so we didn't have to worry about much. But now here we have coefficients different, means here we have 2 and 3, so that will get multiplied along with the means the values. Okay, so let's use the rule number 3, that was the orthogonality theorem. So let's multiply these two terms. So we don't have to worry about the Mulliken symbol here. We will just find out the characters, and then the Mulliken symbol will itself get find. Okay, so let's multiply. So what we will get, 1 into 1 for first E. Okay, then plus, that's 2, this 2 comes from the coefficient of C3. Okay, into 1 into y. Okay, and plus 3 comes from the coefficient of sigma v, into 1 into z is equals to 0. This comes from the orthogonality theorem. So when we will solve it, we'll get 1 plus 2y plus 3z is equals to 0. Similarly, we will again form an equation using these two. Okay, E and the missing one. So let's do it. So it will be 2 into 1. This 2 comes from the value of E. See, these two E are different. This is identity. This is showing the identity element, identity operation. This E is a Mulliken symbol. Okay, I haven't made a video on Mulliken symbol, but I'll be making in future. Okay, so this E is telling that that it is doubly degenerate. That okay, so it's just a Mulliken symbol. So don't get confused between these two E. So this comes from the value of E. Okay, into 1, then plus, and we get 2 from the coefficient of C3, then minus 1 into y, plus 3 from the coefficient of sigma v, 0 into z is equals to 0. So we will get 2 minus 2y is equals to 0. So 2y is equals to 2. So y is equals to 1. So we get y is equals to 1. So we get x is equals to 1 and y also 1. Now if you want to find out the value of z, we have to put the value of y in this. So what we will get, 1 plus 2 into 1 plus 3z is equals to 0. So we will get 3 plus 3z is equals to 0. So z will be minus 1. So the three values of x, y and z are x is 1, y is 1 and z is minus 1. This is only available in option number 3. So the option number 3 will be the correct option. So in this way we have used the Great Orthogonality Theorem to find out the answers. Okay, so in this way these questions are to be done. We'll take few more questions which are asked on the character table. Okay, so let's take this question from CSIR June 2017 exam, and this question was also asked for 4 marks. So the question says that the given below specific rotational mode of BCl3 is plus and minus denoting movement of the respective atoms above and below the plane of the molecule. Okay, this basically says that we have a BCl3 molecule, and it says that these chlorine atoms are coming outside of the plane and this boron is going inside of the plane, and they have given you the character table for D3H point group. Okay, and they are asking that the irreducible representation of the vibrational mode. whether it will be IR or Raman active. The both thing you have to tell. So I will not be solving this question in detail because that will take hell lot of time, okay, and this video will become very large as I want to cover more and more questions in it. So that's why I'm not going to solve this particular question. I'm just giving you, like I have already solved it, so I will just give you the terms which you will get in the in between. Okay, so first thing is that what I have told you, that first you have to find out the total number of degree of freedom. Okay, so the total number of degree of freedom here will be 3n. Okay, if you don't know how to solve the character table, you go, I have given the link for that and you can go to that and watch it. Okay, this is very important. If you will solve, if you know how to solve it, then this question is very easy for you. Okay, just a little bit of trick is involved in the end of the video, in the end of the question solution. Okay, so that I will tell you. So the total number of degree of freedom for this will be, and is the total number of molecules of atoms in the molecule. So here we have 4 atoms, so we are having 3 into 4, that is 12. So the total degree of freedom is 12. This degree of freedom includes the transitional, vibrational and rotational, all of the means all of the rotation means all of the modes. Okay, transitional, rotational and vibrational modes. So in order to find out these things, first of all you have to find out irreducible. First of all you have to find out the reducible representation, then you have to find out the irreducible representation. So in order to find out the reducible representation, you have to write first of all the symmetry operation to C2 C3 3 C2 and sigma H, then 2s3 sigma V. Okay, and then first you have to write the number of unshifted atoms. Okay, so unshifted atoms. So if you'll see, if you'll do the operations, you will see that the number of unshifted atoms here will be 4, there will be 3, 2, 4, okay, 1 and 2. Okay, so in this way, this will be the number of unshifted atoms. Then now the number of the contribution per atom. So contribution per atom. So I have given the formula for it and the values for it. So contribution per atom for identity is always 3, and for all the planes it's always 1. For C3 and C2, you have to find out from the formula 2 cos theta plus 1 and 2 cos theta minus 1. So I'm just writing the values here directly. So it will be 0, minus 1 and minus 2. So the reducible representation will come out to be 4 into 3, that will be 12. This will be 0, this will be minus 2, this will be 4, minus 2 and 2. So this is the reducible representation. Now you have to convert this reducible representation into irreducible representation, taking each character once. Okay, so for A1, like you have to do like this: A1 is equals to 1 by H. H is the order of the order here. So order will be, see how much, 2 plus 1 3, plus 3 will be 6, plus 1 7, plus 2 9, and plus 3 12. So the value of order is 12. 1 by H and then sigma, the product of this and the value given here. Okay, so I'm just doing it. So for A1 is equals to 1 by 12, then you have 12 into 1, so that will be 12, plus 0 into 1, that will be 0, plus minus 2 into 1, that will be minus 2, plus 4 into 1, that will be 4, plus, see, I'm just multiplying the corresponding value with the reducible representation. Okay, so next will be minus 2 into 1 plus 2 into 1. This all I have done in the this all I have told you in my previous video also. So I'm just solving it. Okay, I'm just telling that how to solve. That's it. So it will be 1 by 12. So here we will 12 plus 12 minus 2 plus 4 minus 2 plus 2. Okay, so okay, something I have missed over here. Okay, so wait. Okay, I missed that thing, the coefficient of it. Okay, so it will be so it is, no, it will be 0 only, but there will be 2 also. No, doesn't matter. Now here it will be minus 2 into 1, that will be minus 2, and into 3 also. So here it will be 3 also. Okay, likewise here it will be 4, and there is no coefficient with sigma, so it doesn't matter. Now as 3 we have minus 2 into 1 into 2 also. Okay, now for sigma v, 2 into 1 into 3 also, so we have to write 3 also. So now what we will get, this I should again write it again. So a1 is equals to 1 by 12, then you will write 12 plus minus 6 plus 4 minus 4 plus 6. Okay, so these will be cancelled out and 12 by 12 will be 1, so we get 1a1. Okay, similarly you have to do for all of them. Okay, a2 e prime, a1 double prime, a2 double prime, and e double prime. So when you will do it, you will get the irreducible representation as, I'm just writing. Okay, so it will be, okay, so the irreducible representation will be a1 plus a2 plus 3 e prime plus 2 a2 double prime plus e double prime. So this will be the irreducible representation. Now you have to find out the vibrational representation, vibrational mode. Okay, so what I have told you in the previous video, that you have to first find out the rotational and transitional. Let's find out first the rotational. Rotational is very easy to find out. Just check out in which front of which there will be rz, rx, or ry. So rz is present in the front of a2, so it will be a2 plus, and re, this was given in the in this. Okay, so plus e double prime. Okay, so this is the rotational one. Then write the transitional. Okay, so translational, that will be in the, in which there is written x, y, or z. Okay, so that is given in front of e prime and a2 double prime. Now in order to find out the vibrational mode, just subtract these two from the irreducible. Okay, so lambda vibrational will be, subtract them, so a1 will be like this only because nothing has been subtracted. A2 is subtracted, so that will vanish. E1, from 3 e1 prime we are subtracting 1 e1, so it will be 2 e prime. Okay, then a2 double prime is 1 is subtracted, so a2 double prime and e double prime is cancelled out. So this is the vibrational mode. Okay, now you have to check that this vibrational mode is what is it, uh, like all the three are there, a1. Okay, a1 and a1 prime are both same for this, because prime we apply when that thing is symmetric with respect to sigma h. So a1 is symmetric with respect to sigma h. That's why here for this question, for this character table, a1 is equals to a1 prime. Okay, so a1 or a1 prime both are same here because a1 is symmetric with respect to sigma h. Okay, okay, so now we are having a1 or a1 prime both are same, then 2 e prime and a2 double prime, and a2 prime is not there, so this cannot be the answer. Okay, you have to just check among all these three. Now check out that is your a1, is it Raman active. For Raman active you have to check that in front of that thing you should get like double coordinates. Okay, here like x, y, x, z, or x square, y square. So check for the let's first check out for the e prime. Okay, so for e prime, is it ir and Raman? For ir you have to check here, is it x, y, or z there. Okay, and for Raman you have to check here, that is it double means double fraction. Okay, means quadratic fraction. So let's check for the e dash, e prime. So it is xy also, and this also, though that means it is ir active also and Raman active also. That means this holds. Okay, this holds. Now let's check out for other also, a1 prime, a1 prime or a1. So is it Raman active? For Raman active you have to check it is like quadratic or not. So it is quadratic, so it is Raman active also. So this is also true. Now let's check out for a2 double prime. A2 double prime, is it ir active? So for ir active we only have to check x, y, or z. So it is there, so it also holds. So all these three holds. So now what you have to do in this question, all the three options are correct, but see, this is the only thing which I was talking in the starting, that this is the trick, was the tricky question they have tried to confuse you. See, in starting only they have told that this boron is going inside the plane and these three chlorines are coming outside the plane, and here they haven't mentioned about any axis. So by default we take the principal axis as the z-axis, along the z-axis. So the z-axis is along this. Okay, along boron like this. Okay, so because the c3 axis is the principal axis, so c3 axis is passing from boron, so that's why our z-axis is also passing from the boron. Okay, so it means that the only change is happening in the z-axis, means coming and outside. Okay, and in other things like in xy plane, the things are like chlorine is going inside and outside, so the only change is happening in the z-axis. So that's why we have to consider only the things which is like among all these three in which the z-axis is involved. So for a2 double prime we have the z-axis, so that's why we will take only, and for e1 prime there is no z-axis. Similarly for a1 prime, is also no z-axis. So for a2 double prime we have z-axis. That's why the correct option for this question will be this. A2 double prime is IR active. So this question to be solved. Okay, I haven't solved in that detail, but I hope you will be able to solve this question. All the mathematical work you can do easily if you will watch my previous video. Okay, how to do it in detail. So like this we have to do. Now let's take for a few more questions. Okay, so now here is one more question that is from CSIR June 2016, and the question says the character table for C3 point group is provided below along with the additional reducible representation. So they have given you the reducible representation also. So you don't have to find out the reducible representation, you just have to find out the irreducible representation. Okay, so this is very simple question. I am not going to solve it. Okay, this is very easy, you can easily solve it. Like the concept is very easy, you just have to do the one step and you will get the answer. Okay, so better you solve it, and that will give you some confidence that yes, you are able to solve these questions. Okay, so let's move on to the next question. Okay, so let's take one more last question from December 2016 exam, and this is based on the polarization concept, so that also I want to include in this video, so that's why I'm taking this question also. Okay, so it is given that for H2O molecule, that is for C2B point group, the electronic transition from the ground state to an excited state of B1 symmetry is. Okay, so the ground state over here it is given, so you have to take the ground state as A1 and the excited state B1. Okay, so and they have asked, is it allowed, not allowed, or with X polarization, Y polarization, or we will understand what these things. So in order to do this type of question, if they say you that the transition is happening from this state to this state, you just have to multiply those two states. Okay, and then you have to check that which state you are getting. So they are telling that the transition is happening from ground state to the excited B1 state. That means from A1 to B1. So I will just write it here. So A1 to B1, the transition is happening, just multiply them. So when you will multiply, you will get 1 into 1 plus, means just like that I will write 1 into minus 1, then 1 into 1 and 1 into minus 1. Okay, so you will get 1 minus 1 1 and minus 1, that is nothing but the B1 state itself. So you are getting the B1 state. So now they have asked that is it allowed or not. So like after multiplying, you have to first see that transition is happening between which two states. Multiply those states, the values of those two states, then the value you obtain, just check that which state it is. Okay, here we have luckily got B1 state, so B1 state is the like resulting one. Now you have to check that is in front of that any coordinate is given or not, x, y, or z coordinate it should be. Okay, only single coordinates you have to check. Now whichever the coordinate is given, it will be that polarized only. So we'll see in this case of this B1 that there is like the coordinate given here is x coordinate only. Okay, so that means it is allowed and it is x polarized allowed. So the correct option for this question will be option number 2. Okay, so in this way the polarization questions are done. So I have tried to cover all the types of questions which were asked in previous 2-3 years, or I would say 2-3 like exams of CSIR. So and that's it, that's all for this video. I hope it will help you in like solving questions and in doing problems. And if you have any query, if you want to ask anything, you can ask in the comment section. And if you haven't subscribed the channel, I will request you to subscribe the channel. And thank you for watching, and whatever you want to ask, you can ask in the comment section. Okay, so thank you for watching.